Okay, so welcome back. And so now what we're going to do is we're going to consider this example. Okay, so we're going to use the integral test. And so this is slightly different. So we're going to use a series of 1 over n squared. So again, if we look at the partial sum of this, we get this sum right here. Now, what we're going to do is we're going to compare it. So here's the graph again. So this partial sum, now we've got these rectangles. So I did the rectangles to the left. So from 1, so this, again, we get 1, 1/2, 1/3, 1/4, 1/5, 1/6. Now, notice that all the rectangles are now underneath the curve, okay? So, notice that. Okay, so now, I want to compare the series. So again, the areas of these rectangles represent the terms of the series. So 1 plus 1/4, okay? Right? Oh, hold on a second. Oh, I got these messed up. Yeah, sorry. This, I think about the wrong one. So this should be 9th. This should be 16th. There we go. Okay. So now, so we've got these results. And so now, look, now notice that the graph, okay, of the function 1 over x squared is above the areas of these rectangles. And the areas, again, represent the term. So again, we're comparing the areas of rectangles with the area under the smooth curve. So now, notice that this is always going to be less than, oops. Now this is always going to be less than the integral. Now notice that the integral that I have goes from 1 to k of 1 over x squared. So it starts here, and then I add the 1. Why is that? Incidentally, notice that obviously I can't find the area from 0 because again this goes to infinity, so I'd have to do an improper integral, and so I don't want to do that. We don't have to do that for this proof. So here's the thing. I'm just going to make it equal, right? So I'm going to add 1. So at this point I'm just going to make these equal, and then I'm going to add the rest of it with the integral from 1 to k. So all of this, so I'm starting at 1 to wherever k is, okay? And then I'm just going to add 1 to just match up with the first rectangle, okay? So again, that's not going to change anything. It's still going to be less than, right? So now, what does this mean? Okay, well let's see what we get here. So if we start with s of k is equal to the series, and it's going to be n equals 1, oops, 1 to k, right, of 1 over n squared, not n sub 2, n squared is going to be less than 1 plus the integral of 1 to k, 1 over k squared dx. Now that's going to be equal to what? Well, this is going to be equal to 1. And now the integral of this is going to be what? Well, it's going to end up being what? Minus 1 over x, right? Because you, again, this is x to the negative 2. You increase the power by 1, which brings it to a negative 1. Divide by the new power, which makes it from a positive to a negative. Okay? And now what you're going to do is you're going to evaluate this from 1 to k. All right, now, what does this equal? Well, this is going to be equal to 1 minus what? It's going to be 1 over k minus 1, right? Okay. So now what does this equal? This equals 1 minus 1 over k plus 1, which equals 2 minus 1 over k. So now do you see what happens? So now, what can we say? The limit, right? The limit as what? K approaches infinity of 2 minus 1 over k equals 2. So what we're saying is the partial sums, the sequence of partial sums then for any k, right? So for any k, this partial sum is going to always be less than what? 2. So the sequence of partial sums, so the limit here exists, the limit of this integral as k goes to infinity. In other words, what we're saying is the limit as k goes to infinity of this improper integral, right, is equal to 2. And we're saying that the sequence of partial sums then for all k, right, is less than 2. And therefore, it converges. We don't know what it converges to, right? Well, no, we don't know what it converges to. Okay, we know it's less than 2, so we can't say it converges to 2, but the best we can say is that it converges to some number that's less than or equal to 2. Or, well, actually, I'd say less than 2. Okay? But it does converge, right? So the conclusion is that this partial sequence, so this series converges by the integral test. Can't say what it converges to, but it does converge. That's it. Have a great day.